We discuss three devices, Gunn, an IMPATT diode and also Varactor diode. It may be noted that a Gunn diode is not a diode in the true sense that it does not have any p-n junction. It is essentially an n-type gallium arsenide sample, and we have metallic contacts at the two ends. So, Gunn effect diodes are named after J.B. Gunn, who actually experimentally observed some oscillations in a sample of gallium arsenide biased above some threshold voltage. In 1963, Gunn observed that when applied DC bias across an n-type gallium arsenide sample exceeds a threshold value, microwave oscillations can be obtained whose frequency is approximately equal to the reciprocal of the carrier transit time across the sample. So, this was the experimental observation. Now, the observed oscillations could be understood in terms of the theory presented by Ridley, Watkins and Hilsham, popularly known as RWH theory, which is based on the field induced transfer of conduction band electrons from a low energy high mobility valley to a high energy low mobility satellite valley. So, whatever was observed by Gunn experimentally, this could be explained in terms of the theory presented by Ridley, Watkins and Hilsham. In 1964, Kromer suggested that Gunn's observations were in agreement with RWH theory. So, let us now consider the negative differential resistance based on RWH theory. So, we have gallium arsenide, which is a direct band gap material with Eg equal to 1.43 electron volt, and we can see that the maximum of the valence band and minimum of the conduction band, they are aligned in the EK diagram. Now, this valley in the conduction band, it is called the lower valley L, and in gallium arsenide another upper valley U exists at a slightly higher energy, delta E is equal to 0.36 electron volt. So, to have negative differential resistance, we should have at least two such valleys. In these valleys, the electron effective mass and the mobility are different. In the lower value of the conduction band, effective mass of the electron is 0.068 and mobility is 8000 centimeter square per volt second. So, these are typical values for a given semiconductor, whereas in the upper valley effective mass is 1.2 and the mobility is only 180. So, we see that when the electrons stay in this lower value of the conduction band, they are much mobile as compared to the electrons in the upper valley U. Now, when a bias field is applied in this type of material, the electrons they move to the lower valley and the upper valley U does not have any electron. So, this is shown here. Now, in this region we can see that as the applied electric field increases, the electron velocity increases. This is the average electron velocity or the drift velocity, and Vd is equal to mu L E. Now, as the applied bias field is increased and we have the field greater than a threshold voltage E t, the field is greater than a threshold voltage E t, as we have said that because of this field induced transfer of electrons, we have some electrons migrating to the upper valley. As we keep on increasing the applied electric field, this migration of electrons from lower valley to upper valley continues, and finally at a very large applied electric field, all the electrons they move to the upper valley. Please note that initially the drift velocity increases linearly with the applied electric field, and the slope of Vd EE curve, it is very high because mobility is very large in this lower valley. Here once again, beyond certain applied field, when all the electrons have migrated to the upper valley, we once again get the drift velocity increasing linearly with the applied field, but this time the rate of increase is much lower because the mobility of the electrons has much lower value in this upper valley. In the intermediate region, we find that the drift velocity changes from a high value to a low value, and this rate of change of drift velocity with respect to the applied electric field, this gives negative differential mobility. Here we can see that the slope, the mobility of the electrons decreases. So, in our two valley model, the energy difference between the two valleys must be several times larger than the thermal energy, which is kT and approximately equal to 0.0259 electron volt. Secondly, the energy difference between the valleys must be smaller than the gap energy Eg. We have seen that in gallium arsenide we have Eg approximately equal to 1.43 electron volt, and the energy difference between the valleys is 0.36 electron volt. Electron in lower valley must have a higher mobility and smaller effective mass than that of in upper valley. Now, compound semiconductors such as gallium arsenide and indium phosphide, they satisfy such criteria. We have current density J is equal to Q N V, and that is equal to sigma E. Therefore, dJ dE, that means rate of change of current density with respect to electric field, can be written as Qn dVdE. Now, for negative differential conductance, we must have mu n is equal to dVd dE, and that should be less than 0. We will see that how this negative differential mobility essentially contributes to the operation of a Gunn device. When we have a medium with positive differential mobility, if we have any space charge inhomogeneity caused due to some reason, then this space charge inhomogeneity Q will decay exponentially. So, we have curl of H is equal to del D del T plus J from Maxwell's equation, and if you take divergence on both sides, we can write divergence of curl of H is equal to del T of divergence of D plus divergence of J. Now, divergence of curl of H equal to 0, and therefore, we can write del T of divergence of D plus, in place of J we can write sigma E. So, del T of divergence of D plus divergence of sigma E equal to 0, and therefore, we can write divergence of D, we can write rho the charge density. So, we have del rho del T plus sigma rho by epsilon is equal to 0. So, we have del rho del T plus sigma rho by epsilon equal to 0. Now, a solution to this equation can be written as rho equal to rho at t equal to 0 e to the power minus sigma by epsilon t. In terms of charge q, we can write q of t equal to q at t equal to 0 e to the power minus t by Td. So, Td is equal to epsilon by sigma, which is equal to epsilon divided by n naught q mu e. We substitute the expression for sigma here. N naught is the carrier density, q is the electronic charge, and mu e is the mobility, and mu e is given by d Vd dE. Now, we have seen that if mu e becomes negative equal to mu n, then Td will become negative and Qt, instead of decaying exponentially with time, will start growing exponentially with time. That is, any space charge inhomogeneity will grow with time instead of decaying. And this is very important in the context of operation of the Gunn device, because when the sample is biased in the negative resistance region, we have mu n, the mobility, to be negative, and hence any space charge inhomogeneity present in the sample will grow, giving rise to what is known as high field domains. So, we have seen that when we have a negative differential mobility, then and the device operates in the negative resistance region, a space charge inhomogeneity, if it is present, it grows instead of decaying, and this forms the basis of the operation of a Gunn diode. So, a Gunn device, it is biased in such a way that the field inside the device, it exceeds the threshold voltage. Now, when the device goes into this negative resistance mode, the operation of the device is described in terms of formation of a dipole domain. A dipole domain is essentially a region of electron concentration and depletion. So, such dipole domains are formed near cathode. Now, as the accumulation of charges take place, it also causes a localized enhancement of the electric field. Now, around this dipole domain, we have a high field domain is formed, and that happens with the reduction of field in the remaining part of the sample. Now, this dipole domain formation is shown here, and we have high mobility states on one side of it and low mobility state at the other. This dipole domain actually sweeps across the device, and a new domain can only be formed when this dipole domain is collected at the anode. This is because the formation of a dipole domain is accompanied with a high field domain around it, and when since the applied bias is constant, when the concentration of field takes place near this domain, the field in the rest of the sample goes below the threshold value, and therefore, it prevents formation of another dipole domain in other locations. So, this mechanism of formation of dipole domain, its movement to anode, and this is self repeating. So, once the dipole domain is collected at the anode, we have now another domain formed, and this is self repeating, and we have a oscillation with the period same as that of the transit time through the device. Here we can see that if we draw a line, we essentially have drift velocity at 2 points, but the difference is that here it is in the higher mobility region, here it is in the lower mobility region. ETH is the threshold electric field above which the negative differential mobility comes into picture. Now, this type of Gunn devices are often used as a part of a resonator circuit, and we assume an AC signal is present. Now, depending upon the period of this AC signal, here tau t is the transit time and tau naught is the period of oscillation. So, if the period of oscillation of the AC signal and the transit time, they are same, and during the positive half cycle we have the device biased above the threshold voltage, then domain formation will take place, and as long as the voltage across the device do not fall below some sustaining field, and as long as the electric field inside the device is above some sustaining field E s, the domain will transit through the device and the formation of the next domain will start after the end of this tau naught. But by choosing the frequency tau naught either greater than tau t or less than tau t, we can have two modes of operation. One is delayed mode. Here you can see that even after the domain has reached the anode, the formation of the next domain is delayed till this AC voltage goes above ETH. So, and the opposite case is the quenched mode, when tau naught is less than tau t. So, by choosing a proper resonant circuit for a delayed or a quenched mode, a transfer electron oscillator, it can be made to operate above or below the intrinsic transit time frequency. In one particular mode where the device is operated for most of the time within the negative resistance region, here we can see that the oscillation frequency is much higher, that is tau naught is very less compared to tau t, and several oscillations occur within the same transit time, and therefore, a domain will collapse before it is fully formed and travels to the anode. And by this process, the device is maintained in the negative resistance region for a large portion of time, a basic Gunn type device operating in LSA mode is shown. Here we have this device as a part of a resonant circuit whose resonant frequency is much higher as compared to the intrinsic transit time frequency. Gunn diodes are used as microwave sources, and this is the configuration of a gun which is used, configuration of a Gunn oscillator which is often used as a laboratory power source. So, here we have the Gunn device mounted on a metallic post, and it is enclosed in a cavity. We have a short circuit end which can be made movable for changing the tuning, and also we have an inductive iris present here which couples power to the output waveguide. So, this type of Gunn oscillators are very popular and extensively used in laboratories. Next, we move on to another device, and we briefly discuss the operation of this device. It is an IMPATT diode. IMPATT stands for impact ionization avalanche transit time. So, it involves two mechanisms, one is the avalanche and also the transit time. We know that if a PN junction is operated in the reverse bias condition and the reverse bias becomes very high, then the junction breaks down, and avalanche breakdown is the mechanism of carrier multiplication when the device goes into breakdown. So, it describes the phenomena associated with reverse voltage breakdown of a PN junction diode and transport or transit of charge carrier through a drift region. In 1958, W.T. Reed, he proposed that there would be a phase delay of more than 90 degree between the applied RF voltage and avalanching current if the RF voltage caused the total voltage to exceed the reverse breakdown voltage in the diode. And Reed's prediction was verified later by R. L. Johnson in 1965. So, essentially when the current lags the RF voltage by more than 90 degree, the diode will exhibit negative resistance, and this negative resistance can be used as a source of microwave power if this device operates as a part of the oscillator circuit. We have already discussed that a positive resistance means it dissipates power and negative resistance essentially will deliver power. An IMPATT diode, it contains a heavily doped P region followed by a moderately doped N region and then an intrinsic region and again another heavily doped N region. And we can see that the bias applied here is a reverse bias. The doping profile, the concentration typical values are 10 to the power 20. This is the normal concentration of a p-n junction 10 to the power 16 and the intrinsic region has a concentration of around 10 to the power 13. Now, because of this heavy doping in p region, the depletion region will be mostly in the N region and the electric field distribution is shown here. Now, this is the space charge region. I region is the region through which the carriers generated during breakdown, they will drift, and this region is the avalanche region. Now, here we now consider an IMPATT diode where we have a AC signal present along with the applied DC bias. Now, this total voltage AC plus DC will appear across the device and let it be biased in such a way that P plus N junction breaks when the applied reverse voltage exceeds some threshold value. So, this DC voltage is chosen in such a way that it is slightly below the threshold, and this AC voltage, it comes from a cavity where the diode is placed and the DC reverse bias is slightly less than the breakdown voltage. As we have said that the RF voltage present in the cavity will add to the applied bias. Breakdown will occur when the RF voltage becomes positive and total applied voltage it exceeds the breakdown voltage. When the breakdown is initiated, large number of holes and electrons are created at the P plus N junction. Because of the field, we can see that the DC field, it is acting in this direction, and this field will sweep the electrons across the N region into the intrinsic semiconductor, which constitutes the drift region. So, after a transit time delay, the electrons are collected at N plus terminal. When the time for the avalanche charge build up, avalanche process is an exponential process, it is an exponential growth, plus that for the charge transmit through the drift region exceeds 1/2 of RF period, the output current lags the RF voltage by more than 90 degree, and the diode thus exhibits negative resistance for RF currents. Once the oscillation starts in the cavity, it grows in amplitude until the average negative resistance of the diode becomes equal to total equivalent resistance of the cavity and external load. So, at that time a steady state is reached and the oscillator oscillates in a producing a steady output. The next device we consider is a Varactor diode. We now turn our attention to another device which is called a Varactor diode. A Varactor is essentially a variable reactor. It is a reverse bias p-n junction diode with some special design. Now, when the biased voltage is changed, it changes the device reactance, and in practice the capacitance of the device varies with applied voltage. Now, Varactor diodes are specifically used for frequency tuning of local oscillators. Such diodes are usually made from silicon for RF frequencies and from gallium arsenide for higher microwave frequencies. The simplified equivalent circuit of a Varactor diode consists of a series resistance Rs with a variable capacitance Cj. So, it is essentially the capacitance of the reversed bias junction. Rs accounts for the junction and contact resistances and typically a few ohms. Cj, the junction capacitance, is given by C naught divided by 1 minus V by V naught raised to the power gamma, where C naught is the junction capacitance with no bias. So, when we do not apply any reverse bias, the capacitance that is offered by the diode is denoted by C naught, and V naught, it is 0.5 volt for silicon and 1.5 volt for gallium arsenide. The value of gamma depends on the doping profile of the diode. We know that a junction may be step junction, it may be a graded junction. So, as we have said, the Varactor diode, it is used for tuning in oscillator circuits, and this can be a part of an oscillator circuit where we can apply a voltage to slightly vary the capacitance and thereby tune the frequency of the oscillator circuit. So, in this module we have seen the basics of some of the solid state devices which are used at microwave frequencies for signal amplification or signal generation. We have seen microwave transistors, different types of diodes, pin diode as a control element, Gunn or IMPATT diode which can be used as a part of an oscillator to generate microwave signals. We have also seen Schottky barrier diode which can be used as a detector. So, in the next module, we will discuss the design of microwave amplifiers and oscillators. In fact, we will represent the active devices, the transistors, by their S parameters, and we will see the two-port power gains, stability, design of single stage amplifier, how we can design it for maximum gain, for a specified gain, and briefly discuss about low noise amplifier and RF oscillators.